Uh, Welcome to the first lecture of the day. As always, very happy to have Chiara with us.
Okay, very good. It's good to see you all here early in the morning. So I'm going to start a bit with a recap of the things that I was telling you in the last minute of yesterday's lecture, because it's something very important. So I started introducing the concept of extremal black holes. You think, oh, like this is a bit better, right? Yeah. Maybe? Okay, very good. So I was telling you about like extremality and extremal black holes, which are a particular kind of black holes, which arise when two horizons coincide. So we have seen, for instance, that from the Reisner-Nostrom solution, which is the solution of a black hole in asymptotically flat space, with the presence of charge. In this case, for simplicity, I put presence of electric charge. It is characterized by this matrix here, which is static spherically symmetric, and this matrix admits two different horizons, the inner and the outer horizon, denoted here by r plus or minus. They are at this radial coordinate here, and you can find this by solving like basically for the roots of the warp factor. So this GTT, which in this case is also equal to 1 over GRR. The temperature of the black hole solution that you can compute, as I was mentioning in the past two lectures, from the surface gravity, has this expression here. Like you can alternatively rewritten it in terms either of the black hole charges or r plus and r minus, and it has this. So you see that in order for a horizon, or actually two horizons to be present, like the mass needs to be bigger or equal than Q. Because if this is not, if the mass is lower than Q, then here you have an imaginary value. So you have an imaginary value of the event horizon, and you just want real horizons. So the extremality bound is a bound that tells you that in order for a black hole to have a singularity shielded by a horizon, you need to have this constraint needs to be satisfied between the charges. Let me remind you that also the coordinates, like the real singularity of the solution, is at r equals 0, as in the Schwarzschild one, right? As we mentioned, like the horizons are not real singularities, but are just coordinate singularities. So extremal solutions are solutions that saturate this bound. So here you have greater or equal. The extremal solution is a particular point for which this is, like you have a d equality here. So the mass is equal to the absolute value of the charge. So this is the extremal solution. If you plug in this constraint here, you see that, for instance, this warp factor has a double root. So it becomes a square. And I written down the metric here, which has indeed a double root at this coordinate r equals, like, let's just put it like equals absolute value of Q. That's what I will put in the subsequent formulas. So just to pick up from where I left from the previous let's say, lecture, so from this metric here, we wanted to see how the horizon looks like, how the new horizon metric looks like for these particular configurations. And also, let me mention that when the two horizons coincide, you have that the temperature goes to 0. So it's a particular property of the extremal solution. So the extremal solution, just for what concerns, let's say, semi-classical physics, they're solutions which are stable. So they do not radiate. They have 0 temperature. Nevertheless, they have a finite area of the event horizon. The area of the event horizon, or like the entropy, which is proportional to the area of the event horizon, you can just compute by taking the area of the spatial two section at r equals absolute value of Q. So, okay, we want to see how the matrix look like close to the horizon. And in order to do so, we have to change the coordinates. So we shift the radial coordinate. We expand it basically around the value of the horizon, which is Q. So for simplicity, I take Q to be positive. But like for negative, you can do exactly the same thing. So this is like you perform this coordinate transformation. You do first a rescaling of the radial coordinate, and also a rescaling of the time coordinate, which we denote like new coordinate by t hat. We rescale it by this parameter xi. This parameter xi is an adimensional parameter that we send it to 0 because we want it to zoom in close to the horizon. So sigma goes to 0 defines your decoupling limit. In the sense that when you send xi to 0, you're actually zooming in into r equals Q. So we perform this coordinate transformation, we plug this into this, and then we take the leading term in psi goes to 0, and we get to this matrix here, that also this one, I wrote it yesterday at the blackboard, but just to remind yourself. T squared plus q squared over rho squared d rho squared plus q squared d omega 2 squared. So maybe some of you remember, so this part here is the part that denotes a matrix on the round S2. And then this spacetime here, you remember from yesterday, what is that? ADS2, yes. This is ADS2 spacetime. So the matrix near the horizon is just a product of ADS2 times S2, where in this case we have that the radius of ADS2 is Q, and the radius of the sphere is also Q. So this is a particular property of near horizon geometries of black holes in asymptotically flat spacetime. The radius of ADS2 is equal to the radius of the sphere. If you work with anti-de Sitter black holes, for instance, what we will do in the following in the following class, or I mean, like in let's say half an hour or so, then we are gonna see that these two radii will be different, but we will be able to determine, and there is nothing wrong. The solution is still ADS2 times S2. And this matrix is called the Bertotti-Robinson geometry. Notice that this matrix is very different with respect to the matrix that we get. So this is the matrix that you get at t equals 0 for the extremal solution. Once again, I will repeat this again. So for t different than 0, the matrix that we got was the Rindler matrix, like two-dimensional Minkowski matrix written in Rindler coordinates that read this way, where kappa was the surface gravity of the solution. Sorry, this I forgot, this is t hat as usual. So as again, this is t hat plus d rho squared plus, and we had, like I just put it here, a generic r plus, so this is the radius of the event horizon, and this again, the two element of the two sphere. So again, for a non-extremal solution, so for a solution with temperature, this is like Minkowski 2. And this is the sphere. This has consequences at the level of the physics, because for instance, like you might know that indeed ADS2 is basically an infinite throat geometry. So while this space, like if you turn it into a Euclidean signature, like it's something that is just two-dimensional, like flat space, like this is Minkowski 2, like if you turn it into Euclidean, this is like Euclidean two-dimensional flat space, it's normal. Like this one, this ADS2 throat is an infinite throat that indeed, like, so if you zoom in into the event horizon, you really see that, that an infinite throat develops on the event horizon. This has some consequence because, for instance, if you compute the proper distance of an observer like just outside the horizon to the event horizon, in the case of a thermal solution, the proper distance is finite. However, if you compute it for the ADS2, you see that the distance of an observer, the proper distance that an observer measures to the event horizon is actually infinite. Because you will need to integrate over the rho over rho, that gives you a logarithm, and you have to integrate it from the coordinate of the horizon, that is 0, to R0. This gives you an infinite value. So this means that an observer that is here sees the horizon at an infinite distance. Therefore, this tells you that basically, for an extremal solution, you have some sort of, to first approximation, you have a decoupling of the near horizon geometry with respect to actually what happens outside the event horizon. That's why these solutions are particularly, let's say, like interesting and simple to study. To a first approximation, this is what happens. So you study in the near horizon geometry, which is where you believe that the black hole states reside. You can actually have a feel of the physics without really worrying about what happens outside the black hole. As a last remark, let me also mention, so I mentioned that indeed this is also valid for different kind of asymptotics. And also let me mention that we can also, like starting from this system here, connecting to what I said yesterday, we can also use isotropic coordinates. So let me just put it here. So we can use isotropic coordinate in solving, so if you take the Einstein-Maxwell action that has as solution this metric here, you can do the same. You can solve the Einstein's equation for a different kind of system of coordinates, which is this one. Where this the xi, so I goes from 1 to 3, is just the flat Euclidean line element. So for this one, so the extremal solution, like I put here, is obtained by setting h equals 1 plus q over rho. In this new coordinate, rho is not the same as I put here. Yes. Sorry, x, yes, these are just x, the vector, relative to these 3 coordinates. Yes, sorry, I forgot the arrow. And also, let me put here, sorry, just a moment. So this configuration is also supported by gauge field, which is along the t direction, and is supported also by the other coordinates. And you can find it by differentiating this h, the work factor, with respect to the coordinate, taking the gradient, basically. So the solutions to the, so let me mention. So first of all, the solution that I put there, the extremal solution, the single center solution, is given by this value here, where rho is the square root of the square of like x1 squared plus x2 squared plus x3 squared. But the solution to the, actually to the Einstein's equation are much more general. Needs just to satisfy this equation here, ij, so dxi, so dxj, h of x equals 0. So this means that this function here just need to be a harmonic function of the flat Laplacian. So this means that, so you can also have a more generic, so you can have a h which is made by just one function here, but you can also, like this solution here, so in order to solve the equations of motion, you just have to solve here, and this has many more solutions with respect to this. You can actually superimpose many centers. So a solution of the Einstein's equation is also one that for which the warp factor looks like this, as a sum over many different harmonic functions, like qi over x, sorry, minus xi. So this is just as a curiosity, because this means that actually it's one of the few examples in which the Einstein's equation show the properties that in which you can have linear superposition of solutions. So basically, you can superimpose many different harmonic functions. This is still a solution to the Einstein's equation.
Excuse me, are there 2 different h functions?
No, sorry, it's like always the same one. H and H. Put it this way, yes. So the solution at this point is, yes, it's just static. So you can have indeed, so it's just characterized by one work factor, h, and this work factor, h, is a solution to this equation. Particularly, it can be like this. So it can be also made by, like it can also represent a space-time in which there are many different centers. So this corresponds to centers, like centers with charge qi, so many centers with charge qi at positions xi. Okay, and these are called the so-called Majumdar-Papapetrou solution. That represent a multi-center black holes in asymptotically space, so for which the mutual repulsion due to the charge is balanced by the electromagnetic interaction. So this happens in flat space. In flat space, you can have this perfectly good and very nice analytic solution for which they correspond to many different black holes with different centers placed around that are stable in equilibrium due to the fact that their forces, like the electromagnetic and the gravitational one, exactly balance. So if you remember from yesterday, I told you also that we were using multi-center black holes to model glass phase transition. Well, for that black holes, in order to have a clear holographic picture, you have to work in ADS space. Solutions of this kind in ADS space, they're not known. It's still something which is very much of an open problem, something that many people, including myself, tackled unsuccessfully, but that's something that is still an open problem. Yeah, tell me. Okay. Yes, I can give you this.
So I'm a bit confused. Are those solutions to the full Einstein equations or to
Yes,
the
yes.
perturbed? Full Einstein
It's the full
equations.
Einstein equation. It's
Okay.
a full solution, which is an exact solution. It's one of the few examples in which in GR you can superimpose things, and your solution is still a solution to the equation, to the Einstein's equation, to the full Einstein's equation.
So, but those are like a set of extremal black holes
Exactly.
only.
Yes.
Okay.
Are a set of extremal black holes, all in the same spacetime, that are held together by the gravitational interaction, but they're not collapsing one into each other because they have charge, and this charge exactly balance the gravitational interaction.
I see. So if they were not extremal, then the nonlinear terms and so on
Exactly.
appear.
So
Okay,
these
okay.
solutions are valid. Like here, you can find these sort of solutions only that represents extremal black holes. So you have extremal, so ADS2 throats here and there in the spacetime. You will not find them, at least for sure not, from these equations, like analytically, if you have temperature. In general, temperature spoils the equilibrium condition. So you will need to put other sort of interactions or matter or so on in such a way that they might be there. But with temperature, they're not going to be there.
Thanks.
Are the horizons of this multi-centered black hole given by some simple condition like h equals 0, or it's more complicated?
Yes, I think that. So, for instance, well, okay, you have to really, because this is like I change coordinates in going from here to there. There is not like you see that this is a minus sign and this is a plus sign. So yeah, you will need to just study a bit this kind of equation here. So the horizon will be, I think the horizons are lying at xi actually.
Okay. So this metric is not complete, right? It only covers
Exactly,
the region
yes.
outside.
Exactly. So it describes the region outside these black holes. There was for sure. There was also a paper by, I can point it to you, the paper in which they managed to continue this metric and draw the full Penrose diagram. It's a paper by Hawking, and I don't remember who else, but I can give you the paper.
I see. Okay. And can we also compute, like you were doing in the previous lectures, the free energy for these solutions?
In principle, yes. It's just that you will need to do a specific kind of limit because the temperature for the solutions is 0. So you have to be really careful about taking the good near horizon, like a good. Let's say from the on-shell action, what you get is the free energy over beta, and if beta goes to infinity, you have to take it a bit of a, you have to
But
take
then we
a
would
careful
compare
limit.
the free energy of, say, one black hole versus 2 black holes and see which one dominates and so on.
Exactly.
And this was
So
done.
this was done mostly by by actually Dio and Tarek and collaborators, which are the speakers that will be here next week. They consider that. Indeed, but they consider solutions in the probe approximation. So instead of considering this, they consider a simplified case in which you have a large black hole and different probe black holes. And they check that indeed, if you go below a certain temperature, the free energy of the solution with the multi-center configuration is favored with respect to the single center one in specific phase space regions. I think in general, so the aim for this was to really see at which temperature, let's say, the the multi-center solutions are favored with respect to the single center one, to see that when you cool down the solution, you get actually you get a glassy, let's say a glassy phase. But in principle, I think you could do it also here. In general, people from this solution here, they add supersymmetry and they manage to retrieve their entropy via some supersymmetric index. So I guess that is more something that people were more interested in that other than computing like thermodynamic quantities like the free energy and so on. Yeah. But so yes, so this, all I'm saying is that the solution here, they have relevance for this sort of like glassy picture, and also they have some relevance for the microstate count in asymptotically flat space. I'm not gonna talk about flat space a lot in these lectures because I will focus on ADS black holes, but you can ask questions and I'll see if I can answer.
I have a question. So if we can use linear superposition here, means that if we have supersymmetry, we can also do that, right? In asymptotically flat space-time, but in asymptotically ADS, can you use that superposition principle, or is it not possible with BPS state?
No, for if you have the equations of motion of Einstein-Maxwell lambda, you cannot rewrite the equations in this way, and then you cannot solve them just by this, with a superposition principle.
So that means that BPS condition get more complicated?
Yes, for sure it gets more complicated. That's what I will show you in the next class. But just even without supersymmetry at the level of equations of motion, in ADS space, the presence of a potential spoils the equilibrium condition. Of course, you have a potential that pushes the center together. So in a way, you already expect that some equilibrium condition will be spoiled, and supersymmetry doesn't seem to help you in this regard, at least not from what we know now. Of course, this is still finding these solutions in ADS space, maybe with other sort of interactions, matter fields and so on, might be possible, but so far nobody has managed. Okay, so this was a bit of an aside, but just connects a bit with the picture that I showed you yesterday about this glassy physics. So in the remaining of the lecture, so I will focus on a particular class of black holes, which are the supersymmetric black holes. So in general, for being supersymmetric, also like being extremal is something that you need to be supersymmetric in flat space. So extremal, and you can, let's say, you have to, like a black hole can be, has to be extremal and then can be supersymmetric. So if a black hole is non-extremal, it cannot really be supersymmetric in asymptotically flat space. With some caveat. If you want, I can explain also the caveat. If you consider pure solutions which are purely real. If you allow yourself to be in a complex black hole solution, you can have very strange things. I can explain a bit more. But in general, being extremal is a requirement for being supersymmetric in flat space. Something kind of similar is happening for asymptotically ADS space, but not quite. So in ADS space, you can have supersymmetric configurations which are also have a naked singularity. And they are the simplest solutions that they are there. It's something that I will discuss in the lectures, but these solutions can then be dressed, like with matter fields, for instance, scalars and so on, to have a good event horizons. Good event horizon. And this one were the object of the first microstate counting via localization like studies. But okay, so I will start from the beginning. So I did not assume that many of you were familiar with supersymmetry. So I will give a very, very simple lightning review of supersymmetry. Who is, like, are there people which are familiar with supersymmetry? Okay, a bit, not that many. Okay, so I'm gonna give a very, very gentle introduction. So you will see that eventually, once I will tell you how to construct supersymmetric black holes, you will need a very few ingredients. But just to give you an idea of I will give you a bit of a review on supersymmetry just to give you the general reference. So first of all, let me just erase this thing. Okay, so for supersymmetry in general, so I'm gonna give you, well, reference, for instance. So supersymmetry. If you're looking to start doing computation in supersymmetry and so on and so forth, I would suggest you, so there are many, let's say, reference textbook, like probably the most famous one is the Wessenbagger, Supersymmetry, Supergravity. But like when I was doing my master, just to keep a bit of like, to start doing a bit of computation, I would suggest the review by Martin. And it's called a supersymmetry primer. And you can find it on the archive. But okay, so what is supersymmetry? So supersymmetry is a symmetry that relates bosons and fermions. So in supersymmetry, you have an operator, which is called a supercharge, which I will, so by the way, I will shorten supersymmetry with SUSY, just to be a bit more like compact, that acts on fermions and turns them into bosons. And the same one, like, acts on bosons and turns them into fermions. So supersymmetry was in general like, so the first, let's say the first motivation to introduce supersymmetry is basically to, like, it as a computational tool, let's say, because supersymmetry, due to the fact that like supersymmetry algebra is such that like matters comes into supermultiplets, and in general matter is packaged in these specific supermultiplets in such a way that the degrees of freedom of fermions are equal to the degrees of freedom of bosons. So in general, this in your theory leads to cancellation. For instance, one of the reasons why, let's say, supersymmetry was first introduced was, for instance, in the standard model. Indeed, you have like loops that renormalize, for instance, the Higgs mass. This is very schematic. For instance, this is like a fermion. The contribution of a fermion to the Higgs mass, and a contribution to, let's say, additional scalars that indeed that enlarge the standard model. Delta MH to the scalar. They have pretty much like a similar, let's say, a similar form. And supersymmetry, like a supersymmetric model, will guarantee basically, like, will have couplings in such a way that the contributions, for instance, for loops, so divergences coming from fermions, would exactly cancel divergences coming from the bosons. In this case, scalars, but it can be some other bosons sitting in supermultiplets. So in general, supersymmetry guarantees you the fact that your theory is well behaved because there are some cancellation. So you can do your computation, let's say, in like a tree level, and you're kind of sure that supersymmetry ensures you the fact that like the loops should cancel. So in general, the operator that then turns fermions into bosons, like the operator that generates transformation that relates bosons and fermions should be a spinor. It should carry spin 1/2. So the operator Q should carry, so it should be an anti-commuting spinor. Well, okay, let me just put it later for the in the algebra. Okay, carries spin 1/2 and generates this kind of transformation. And the supersymmetry algebra that in general one works with has this form here. Supersymmetry algebra is highly constrained by known theorems, but schematically it has this form. It has like the generator of supersymmetry squares on the momentum, the 4 momentum, and then again you have these other commutators or anti-commutators in general that are 0. Dagger equals 0, and also the supersymmetry commutes with the momentum. I'm being very schematic here. I will, yeah, of course, if you want more detail, you should check the various literature. I can give you even more specialized textbooks. Sorry, this is like, so these are, it's very schematic, but what I'm saying is that this should be a contribution, for instance, to the mass of the Higgs from a fermion, and this is, again, the contribution to the mass of the Higgs from a scalar. This is very schematic. I didn't tell you but if you compute this thing with a cutoff, this is proportional to the cutoffs. Like, okay, I can write it down, but I didn't want to dwell too much into it. This is something like a coefficient, lambda UV squared, and this from the scalar is another coefficient, so coefficient 2, let's say. Again, lambda UV squared. Supersymmetry ensures you, I'm being very schematic, that these two coefficients somehow cancel. So the loop corrections are just collapsing. Okay, so also here I'm being very schematic and for sure not exhaustive, but I'm just going to give you the ingredients that you need to understand what happens later in the lecture. So in general, so you have this operator that transforms fermions into bosons and vice versa. So a single particle states, like of this supersymmetry theories, fall into irreducible representation of the supersymmetry algebra. And so supermultiplets are just building blocks of the matter of your theory that you have. So they contain some matter, depends on how many supermultiplets, you have different matter content of your field. And each supermultiplet, for instance, contains like bosons and fermions, which are super partners of each other, which are related by these transformations here. And in particular, each supermultiplet contains the same amount of degrees of freedom of bosons and fermions. For instance, I'll give you just a very simple example. Let me just erase it here. So each supermultiplet has equal number of bosonic and fermionic degrees of freedom. So for instance, in general, so this is for p mu different than 0. I will come back to this point later. So for instance, a supermultiplet, it contains like a massless spin 1/2 fermion and a massless spin 1/2 boson. So it's just a gauge field. They both have on shell 2 degrees of freedom, so 2 fermionic degrees of freedom on shell. Also this one, 2 bosonic degrees of freedom on shell. And this is the so-called gauge supermultiplet. Supermultiplet. You also can start, for instance, from a complex scalar field, like 2 degrees of freedom, acting with an operator of spin 1/2, give you a massless spin 1/2 fermion. And this will be the chiral multiplet. But just to give you an idea, so for each supermultiplet, you have something in which like you start from a particle with particular spin, and the action of the supersymmetry generates another particle with spin which is increased by 1/2 with respect to the one that you have started from.
Is it necessary that both are massless or both are massless?
No, you can, in theories of gauge supergravity, you will see that actually the mass are not the same.
Okay.
So it's not quite, it depends a bit on the model, depends on the algebra. But for sure in theories of gauge supergravity, okay, these I'm a bit running ahead, there will be gravitini and gaugini that will have mass. But okay, so in general, you have 2 parts. So in this case, it depends also on how many supersymmetries you have in your theory. But in general, each operator that you have raises the spin of the particle, the first particle that you have, by 1/2. This is if you have theories with 2 supercharges, then you have that the whole tower, you have spin 1/2. The first charge takes you to spin 1 and another spin 1, and then the action of the second charge takes you to spin, for instance, this case is 3/2. It's a bit of a bad example, but it takes you like in jumps of spin 1/2, let's say. So in general, so this is like just a supersymmetry, just like a symmetry by itself. So we are going to work with theories of supergravity. And as you can imagine, so supergravity means that you work with general relativity and you incorporate like a supersymmetry in it. So it means that indeed, so first of all, like in general, like in formal terms, it means that you're promoting supersymmetry to a local symmetry of your theory. So you have, like in theories of supergravity, you have GR and you implement supersymmetry in that. So your field content will for sure have a graviton. That, of course, is spin 1/2. But also the super partner of the graviton will be a particle which is called the gravitino, which has, sorry, this is spin, okay, you should have told me, spin 2, right? Spin 2, and the gravitino is spin 3/2. So it's the so-called, like it's a fermion, but it satisfies the Rarita-Schwinger equation. It's a spin 3/2 particle. And this corresponds to you, this is so-called the gravity multiplet. So in general, so to repeat once again, whenever you have supersymmetry, you have that to each particle correspond a super partner of spin that differs from, in general, 1/2. So, okay, so supergravity arises then, like we are very interested in, because supergravity arises as the low energy effective theory for theories of, like for superstring theories. So in general, what I didn't tell you in this whole thing is that in order to have, let's say, consistent microstate counting, we need to work with precise holographic dualities. In particular, what we will work with, so the supergravity theory in consideration. So we're going to work with 4-dimensional supergravity theories, also here abbreviated with SUGRA, supergravity. So that will arise as a truncation of M theory. So this is our better 11-dimensional supergravity on 7-dimensional manifolds. So for instance, 7-sphere. So these particular supergravity theories that we're going to work with will have an ADS4 vacuum. So we're going to work with ADS4 black holes, which will have a holographic dual in a superconformal field theory in 3 dimensions. So in order to make use of the duality that relates indeed the ADS4 to a CFT3, you need to work in theories which have an embedding in string theory or M theory. And that's why I'm working with theories of supergravity in 4D. So in general, so I will show you a very simple example of supergravity in 4 dimensions. But before doing this, so, and I will tell you what are the conditions for a black hole to be supersymmetric in these sort of theories. But before doing this, so basically, what I will need to do is so the solution for sure will need to solve the Einstein's equation. So a solution is a solution to the equations of motion. So there will be a black hole that satisfies the Einstein's equation, but there will be also additional constraints imposed by supersymmetry. So the fact that your solution preserves supersymmetry, so for instance, if you have a black hole which is SUSY, so say a supersymmetric black hole, will have these 2 properties. So first of all, it solves the Einstein's equation of supergravity, but also we have to impose on top of it constraints. We have to impose the fact that the supersymmetry variations of the fermions are 0, and the supersymmetry variations of the bosons are also 0. So this means that your solution is supersymmetric. And I will tell you also, I will explain you like very explicitly what this means in terms of supersymmetry variations. So this will mean that, for instance, if you have a solution that generalizes this one, imposing these two conditions here will basically give you some constraints between the various parameters. Which one, sorry? You mean which one? This one? Or okay. So here, so I wanted to just set the stage for the theory that I'm gonna work with before. So in the future, so in the next let's say half an hour, 40 minutes, I will tell you how to construct black holes in ADS4 space that preserves supersymmetry. Why I want to do so? Because I want to give a microscopic interpretation of their entropy. And in order to do so, I want to map the black hole system into a system where I can actually count states using holography. This system, where I will be able to count states or to compute a partition function, will be this theory here, this three-dimensional conformal field theory with a lot of supersymmetry, lots of bells and whistles, but it will be a theory without gravity. This correspondence between something, okay, between ADS physics on ADS4 and this particular theory is valid only if you have, let's say, supersymmetry. And in particular, it relates M theory. So let me just put it in this way. So this kind of ADS4 CFT3 duality relates M theory on S7 to a particular theory which is called ABJM theory. I meant to explain this when I go to the field theory part. But basically, this is a particular superconformal Chern-Simons matter theory. And this particular ADS4 CFT correspondence is very well established. There are some string theory constructions. This is like a duality. It's like the equivalent of the duality that basically relates type 2B superstring theory on ADS5 cross S5 to n equals 4 super Yang-Mills. I think this is the prototypical example of ADS CFT, involves ADS5, like type 2B string theory, and n equals 4 super Yang-Mills. For simplicity, just because I think it's the first, let's say, microstate counting that was successful were found in 4 dimensions, I decided in this lecture to focus on the duality in 1 dimension less, which relates, instead of relating ADS5 and CFT4, relates ADS4, CFT3. And so I will need to deal with black holes which are supersymmetric in ADS4. So I will deal with theory of supergravity in 4 dimensions that come from M theory on the sphere, because this is what the duality, the starting point of the duality. Is that clear, maybe? So I guess that you would have seen maybe aspects of duality between, n equals 4-dimensional super Yang-Mills and ADS5. Maybe that's the prototypical example. Yeah, the duality here goes pretty much the same way. It just relates theories in 4 dimensions to this theory here, which is a 3D Chern-Simons theory. I will give you, not so much specification, but so it's a theory which has a coupling of the form. I always forget. Let me just fish it out. Always unsure of the coefficient, but basically, this is made by 2 copies of a Chern-Simons theory. I don't want to go too much into detail now, but there's a coupling of this form, A wedge dA plus, 2/3. That's the coefficient that I'm never... so basically, this theory here is a very complicated theory with supersymmetry with 2 copies of this coupling here with UN gauge group. But this has an exact duality that relates it to M theory on S7. Alternatively, to type 2A on CP3. But okay, let's not get into detail that. For these lectures, you just need to know that the setup that I'm working with will be supergravity on this like on 4 dimensions that arise from this sort of setup, which allow a direct mapping into a theory that we know how to handle. Yes.
Thank you. What is the feature of the theory on the other side of the correspondence that allows to count states?
The feature, yeah, so it's a, let's say, it's a theory with supersymmetry, and I'm gonna just briefly mention or briefly show you that there are some techniques which are called supersymmetric localization, which allow you to perform the computation of the partition function exactly in this sort of theories. They're not the only theory which are amenable to localization, so other theories are there, but it's something that is the prototypical example for which we can do computations.
Okay, thank you.
There are also other sorts of dualities of this kind that instead of involving 7-dimensional sphere involve more complicated Sasaki-Einstein manifold. But for the moment, we're gonna restrict it to this. So supersymmetric localization, you can also use it in n=4 superior mills, in other examples. But in particular, it applies to this case, which is something that is the object of these lectures. Okay, so let me just go through it. I will promise that actually the supergravity theory that we're gonna work with will be actually very simple, so don't be scared. So the supergravity that we're gonna consider will be n=4 minimal gauge supergravity. So minimal already tells you that it's something that should be simple, right? So it's actually the bosonic action of this theory we have already known it, like we have already encountered before. Because the bosonic action is just Einstein-Maxwell lambda. So for the minimal the full name is for the minimal Fayet-Iliopoulos Billion gauge supergravity, but let's just abbreviate it into this. So the bosonic action of this theory is very simple. So the Lagrangian is really something that you have seen it before, right? F mu nu, F mu nu. This is Ricci, Maxwell. And also I have rewritten the cosmological constant in terms of this G. This G parameter is called the gauging parameter. So I'm gonna, and this has the relation. So this is related to the cosmological constant. And this is less than 0. So this particular theory, so the bosonic action is this, but as I was mentioning, the fact that you have supersymmetry means that you also have fermions. So to this particular action here, you need to supplement it with fermionic terms, which I'm not gonna write down, but for instance, well, in full generality, but for instance, you will have a term which involves the gravitino. For our purposes, the black hole solution that we're gonna study, for them, we will set the fermions to 0. So actually, the fermions will not play any role in the equations of motion. But so this sort of theory and the black hole solutions were studied many, many years ago. So first by Romans in '92, in a very beautiful paper that has lots of things. And it's also the first paper that I studied during my PhD. And it's also a very nice and very simple paper. So I think I suggest that if you want to study a paper on this, I think this is a very good reference. So the super multiplet, so we are minimal gauge supergravity, meaning that we are restricting the amount of matter to the minimum possible. So we're gonna add only, so we are gonna have only one super multiplet. So we're gonna do also this supergravity n=2. So it means that we are gonna deal with theories with two supercharges. So the super multiplet is composed by, so first of all, the super multiplets needs to have the graviton, right? Otherwise, it would not be a theory of supergravity. So first will be graviton, so spin 2. So this G mono. Then again, the same supermultiplet, you act with a supercharge. In this case, I did it in a reverse order, but basically you have like 2 gravitini, which we assemble into a complex one. So 2 gravitini that I put here, we're gonna assemble into just one. And then by making it act with the other supercharges, we're also gonna have a graviphoton. So 1 graviphoton. Graviphoton is nothing else other than a gauge field. So you have spin 2 particle, spin 3/2, and spin 1. Because we have n equals 2, that really makes you 2 bumps into the spin. So you have all this matter, which is, in a way, like the bosonic action is very simple. So you have the term for the metric, the gauge field, and then also you have the cosmological constant term. I can delve more into the structure if you want. Maybe you can do it with the exercise, but I'm going to give you just the essential detail for you to understand the basic, let's say, basic computation. So indeed, the super... Sorry? It's fine. It's like I could call it photon. It's just that in general, it sits in the gravity multiplet. So in general supergravity theories, you have also other matter. In more general theories, I will have also scalars, other vectors, and so on, in order to distinguish the vectors that you have in other multiplets to the vector that comes because of the supermultiplet of the gravity. I call it graviphoton. But it's just a nomenclature. It's just a gauge field. Yes? Yes, should be maximum supergravity. I'm just reducing it to a very small subset. Then I can embed it into maximal n equals 8 supergravity, but I'm just going to restrict to the minimal amount of supersymmetry to just retain the basic features, let's say. But all like the black holes that I'm going to study here, their structure can readily be seen also in n equals 8, let's say, with appropriate modifications. But the juice is the same. So the supersymmetry like transformation relates bosons and fermions. And in general, so I can write down, so this action here, I wrote here the Lagrangian, but of course if you take the action, like theory of supergravity means that the action is invariant by supersymmetry variation that turns bosons into fermions. So this is an invariance of the action. So I'm gonna write down here what are the supersymmetry variations. So I was mentioning the supersymmetry variations turns bosons into fermions. And for the black hole configuration that we are going to study, we want configurations which are very simple. So for simplicity, we consider only bosonic configurations. So we set the fermions to 0. So the fermions will not have any roles in the equations of motion, but will have an implicit role because we will need to set to 0 the supersymmetry variations of the fermions. So let me write it down. So supersymmetry variations of bosons is something that are functions of fermions. So for our solution, since we set the fermions to 0, will be automatically 0. I'm not going to write that down. So what we will need to worry about will be the supersymmetry variations of the fermions. And the fermions in the game are just the gravitini. So the supersymmetry variations of the gravitini, delta psi mu, read like this. So I'm going to put it here in full details. So you have a term with the derivative, a term that involves the spin connection, sorry, maybe I rho sigma. So the supersymmetry variation, so these are the supersymmetry variations of the fermions that, as you know, like it involve, like as you see here, involve in particular like terms with the metric that is included in the field binds here, and also the graviphoton, so the gauge field here. It's in general a general feature of supersymmetry that the supersymmetry variations of fermions are like involve the bosons, and the supersymmetry variation of bosons are functions of the fermions. Because indeed, the supersymmetry relates bosons, transform bosons in fermions. And in this supersymmetry variation, you find that like the supersymmetry variation is parameterized by this parameter epsilon, which is a spinor that parameterizes indeed the amount of supersymmetry that your solution preserves. So this is the parameter of your supersymmetry transformation. Yes. In our solutions, so for finding explicit solutions, I'm going a bit fast, but in finding our configurations, I will set the fermions to 0. It's like if I solve my equations of motion by setting all the fermion fields to 0. In solving, so I didn't write you here, so this is like part of, there will be other pieces of the Lagrangian and so on. Yeah, the classic, I'm just solving here things at the classical level. I'm solving the Einstein's equation, and I supplement it with this particular additional property, which tells you that your solution preserves some supersymmetry. So I can solve my Einstein's equation and the equation that involve the gravitino by setting the gravitino to 0. But even if the gravitino is 0, I still need to set the variations of the gravitino to 0, and this is a function of the bosons. Maybe I'm going a bit fast, but I had to introduce many concepts here. But for your purposes, what you like, let's say, what you are mostly interested in is that we are working with a theory of supergravity, which really looks like Einstein-Maxwell, but it's supplemented by additional fermions, this one. In order for your solution to really have some particular property of preserving supersymmetry, it needs to first solve the Einstein's equation, but also I want to make sure that the supersymmetry variations of the fields in my configuration, for the black hole configuration, like their supersymmetry variation is 0. The supersymmetry variations of the bosons are 0 automatically, because I set the fermions to 0. But for the supersymmetry variation of the fermions, I need to do some more work, because their SUSY variations depend on the bosons. Yes, so here, so I didn't define any terms, of course, it's like, so it's a bit, I see that there are lots of details, but these are all the terms that are, so they are really, I can give you that's a deeper meaning. There is some geometrical construction that tells you what are the supersymmetry variations based on which kind of Lagrangian you have. Because indeed, like supergravity has some inner structure, like here minimal supergravity, but in general, in this gauge supergravity, you have that a subgroup of the R symmetry is gauged. So the gauge coupling constant that you have here trickles down into these expressions here. These couplings are all fixed. The numbers that you find here were found by many people before me, and they are very much set in stone. If you fiddle here, if you put other coefficients, you will see that actually your action is not invariant under supersymmetry anymore. So these things are fixed by the geometrical structure of supergravity. So what we are left to do is that we want to set the supersymmetry. So first, again, solve the equations of motion, and then set the supersymmetry variations of the gravitini to 0. So we are going to work, so we know what are the solutions to the bosonic action of this theory here, because we find it in the first class, right? So we have the bosonic action is Einstein-Maxwell. So it means that the static and spherically symmetric solution that we're going to work with will be the ADS Reister-Nordström black hole, right, with charge, which has this formula here. So the solution that we're going to deal with will be static and spherically symmetric black hole, whose warp factor I'm rewriting in this way. So we already define Z as Q squared plus H squared. And Q and H, they are just the component of the gauge field. So I've just rewritten the ADS Reisner-Nostrom solution. Ah, sorry, yes, indeed. So in doing this, let's see. So in order to, let's see how to put it. So in order to couple fermions to general relativity, I'm using the Filbine formalism, or it's also called the tetrad formalism. Are you familiar with this formalism? So when you couple fermions to gravity, you need to ensure, invariance under Coordinate transformation and also local Lorentz transformation. And you encounter problems because basically the group of that you have, like, the group of diffeomorphism, coordinate transformation, like they are continuous, basically does not admit spinorial finite dimensional representations. So you have to split your invariance between, let's say, local Lorentz invariance and diff invariance. It's a lot of theory now that I can explain a bit more, but basically what happens here is that in my computations, I use some fields which I call the tetrad field or the Filbine. So they are objects which satisfy these properties with this property here. Maybe I'm gonna write it here. This happens, you always need to use these objects when you want to couple fermion to general relativity. And so they are objects which are somehow a bridge between, let's say, local Lorentz transformation and diffeomorphisms. So the Filbines are fields that satisfy this equation here. Let me just put it. So the metric G mu nu is equal to E mu A, E mu B, eta. So this is the Minkowski metric. Eta AB is the Minkowski metric. So it's the metric which is -1, 1, 1, 1. Okay? And then the metric, the graviton field that I'm gonna write down, it's this one. So when the metric is diagonal, basically this E mu A will have, well, let me write it down. So for instance, E 1, 1 will be square root of V. So you can find your Filbine is like it's a choice that you made of Filbine, but you find these objects here in such a way that contracted with the Minkowski metric gives you the curved metric. Okay? So whenever you see a gamma, so the gamma matrices with the flat, with indices A and B pertain to the flat metric. So indices which are AB, like not Roman indices, they are raised with the Minkowski metric, while indices which are mu, so these Greek indices, they are raised with the spacetime metric, this one. So when I write gamma mu, you have to think about as E mu B gamma B. Okay, where these gammas are the usual gamma matrices whose anticommutator, so these gamma matrices here are matrices such as gamma B, gamma A, gamma B equal to 2 eta AB. This is something that you have seen probably, like these are just the generators that you, you have when, for instance, you see how a spinor transform under Lorentz transformation. These are the gamma matrices here. Sorry, this is like the anti-commutator. So whenever you see gamma mu, it means that it's contracted with a Filbine. Okay. So for instance, this one is contracted with a Filbine, but these ones are not. And these are the components of the spin connection, which is also like the gauge field, like that arise, for instance, if you have the Dirac equation for a spinor in curved space, this will be the connection term. But yeah, okay, there is a bit of, so yeah, I skipped to a bit of formalism, but in general, yes, whenever you have to couple fermions to theories of gravity, you have to go through this sort of machinery. So, okay, coming back. So this is a solution that we have seen it very like in depth, let's say. And so we want to see, this is a solution to the equations of motion. We want to see for which parameters, m, z, and so on, you can preserve supersymmetry. And we're gonna do it by seeing actually how this condition is satisfied. And so I'm gonna give you also a bit more details in here. So I give you how they are defined, the gamma matrices, and so on. I give you also, so which shows Filbines. So the Filbines are defined by that one. You can make different choice of Filbines. We'll do it the simplest one, which is choosing the Filbines to be diagonal. So our Filbine E mu A will be diagonal. U minus 1, R sine theta, where we define U to be square root of B. So B of R. Okay? And also, what we can do is, for instance, I'm going to give you here, so then you can also do the remaining component of the exercise. I'm going to compute the components of the spin connection that has non-zero component, which read this way. So these are just the things that we need to input in order to see in which way this is satisfied. So maybe like it was a bit of a long machinery, but what we need to do is that we know that this solution solves the Anson's equation. We're going to plug this solution here with these choices of Filbine there. We're going to put it inside this equation here, and we're going to see for which parameters you manage to solve this equation here and manage to make it equal to 0. In this way, it means that your solution will preserve some supersymmetry.
Maybe a basic question. So you have the Einstein-Hilbert equations.
Yes.
And then you propose these ansatz because we are looking for a black hole. We get this solution, and then we want to check SUSY. Is this the most general black hole solution that we can have in the way that a black hole can always be written as a blackening factor BR on the T component and the other thing on R, or we can have like something that also involves the sphere?
In general, you can have we are focusing now on static and spherically symmetric. Of course, you can have, for instance, rotating black holes. You can have black holes with a different kind of horizon. So here, I put the horizon to be a sphere. In ADS, you have also black holes for which this is like a plane, or it also is hyperbolic space. Then you can compatify it. So for the moment, I'm choosing this one because the solutions are very easy, and then we can really see how to, I can give you a clear example on how to solve this. But yes, it's not the most general solution, but it's like the simplest one because already this thing is kind of complicated. So for all this, I'm going to give you a prescription of how to solve the Killing-Spinor equation. And at least once in your lifetime, you can say that you solve and you find a Killing-Spinor. This is something that you can also use in many other, let's say, in other computations. But at least this is a very clear-cut example. So I give you here all the data, field lines, spin connection. Now we are going to start solving. So solving the Killing-Spinor equation means that we need to impose omega. Yes, I have the definition here. I didn't put it. Okay, I can put it here. Let's say omega comes from the fact that basically from the torsionless condition. Gamma sigma mu sigma b minus e nu b d mu. Okay, sorry, I need to erase this thing. E a nu. Okay, these are contracted. This BA. Okay, so this comes from this. So once you have all these formulas of the geometry of the field bands, the torsionless condition that gives you the spin connection in terms of the field bands, then you have all the ingredients to plug it into the SUSY variation. As I mentioned, this thing, at least you see it once in your lifetime, the one of you that don't do supersymmetry, but I think it's a very nice example, and it's something that then you can, if you know the, let's say the technology now here, the procedure, then you can apply it to many other things. So what do you need to do in order to solve this Killing-Spinor equation? You know, there is a parameter epsilon. So parameter epsilon is, at this point, arbitrary. So a recipe for solving the Killing-Spinor equation is that you have to impose projections on epsilon in such a way that the various terms talk to each other, right? So these terms here with the gamma mu, gamma rho sigma, and so on, in particular, like since gammas give, like they are just like all these gammas give a basis for, basically they are all independent. It's not really said that these terms talk to each other. What you need to do is to impose projections on your spinor here in such a way to make these terms talk to each other. And then, once you do that, and you manage to get things to work, read off the constraint on bosonic fields. So we decide to first, given the fact that the spin connection here has only one term for the theta component, we start, for instance, from the theta component of the Killing-Spinor that reads this way. So we plug everything in. So let's say theta component here. So we start from d theta epsilon minus 1/2 u gamma 1, 2 plus 1/2 gr gamma 2 plus I over 4 r f slash gamma 2, where the f slash is just the contraction of the, like f mu nu, gamma mu nu, and this is h gamma 2, 3. So I've already assumed now, so I skipped one part, but let's say for simplicity, I'm assuming for the moment no electric charge, because you see that the simplest solution is purely magnetic. I will tell you now. So we see that this, sorry, I also forgot here because this is always like the spinor here. So we need to impose this equation here equals to 0, right? The point is that here you have, for instance, gamma 2 epsilon. This is arise with another gamma 2, 3. You have what? Flat. Yes, I stripped off all the field lines. So when you see, for instance, this term here, I put R because you see here you had gamma mu, so gamma theta, and the field. Okay, fine. For now, yes. Actually, no. It's for now. It's an undetermined spinor. It can have a radial dependence, it can have dependence on the coordinates, but it's undetermined. Yes, 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 but you promote, in supergravity, you promote supersymmetry to be a local symmetry, so the parameter depends in general on the coordinates. Yes, it's a lot of notions. I can agree on that, but we are getting there. At least you will see one example very explicitly. So this is one of the components of the Killing-Spinor equation. As I was mentioning, we need to impose projections on epsilon. So I'll define my projection as something like this. So I define a projection which is called P, which is 1/2, 1 plus gamma, where gamma can be whatever gamma you want. So this projection has the properties that it's really a projection such a way that P squared equals to P. So Romas had the beautiful idea, so he stared a lot of this equation here, and what he found out is that we can impose two different projectors on the Killing-Spinor, and actually all the equations kind of collapse very nicely. So now I need to write down the projections. So the projection that we are going to impose will be this one. So P. So these are projections that we impose on the parameter epsilon equals 0. First projection, and the second projection would be P gamma 1 equals 0. So in more explicit terms, it means that whenever we see minus I gamma 2, 3 epsilon, we can then substitute it with epsilon. That's the meaning of this projection here. And the same thing. Exactly. Yes. So yes, let me just write it. So P of big gamma. So, and the same way, when I see this, it means that gamma 1 epsilon is equal to epsilon. So whenever I see in the Killing-Spinor something which has a gamma, then I can use this relation here to simplify this equation. So okay, it's a bit unfortunate that I wrote it here. So I'm gonna erase this line and I'm gonna report here the equation that we are gonna manipulate. Hopefully I didn't make any typos, but you never know. So okay, this big equation, so we just report here d theta epsilon minus 1/2. So I report here the big warp factor, which is g squared. So this is square root of v, which is the warp factor, so it's u. G squared r squared plus 1 minus 2m over r plus h squared over r squared. And then I have gamma 1, 2 epsilon. And then I have plus 1/2 gr gamma 2 plus I quarter r 2 over r squared. I'm just plugging in this thing. Gamma 2, 3, gamma 2 epsilon. And this I have to impose that it's equal to 0. So now we are in a place that we can manipulate, for instance, these gammas here in light of these relations, right? So first of all, this one, we know this thing, we can just erase it and then set it minus gamma 2, 1, right? Because of the property that gamma matrices anti-commute if their indices are not equal. So for this one, then this is like having gamma 2, gamma 1 epsilon, so this is again with a minus sign, but we know that gamma 1 epsilon is equal to epsilon. So we use this condition here, that it means here that we have, sorry, I think I missed a minus sign, okay, it's like here. So this is equal, so given this chain of manipulation, it means that this is equal to plus gamma 2 epsilon, okay? So I first use the fact that these two anti-commute, so then to kind of, to exchange the order, this gives you a minus sign. I use this projector here, such that minus gamma 1 epsilon is equal to epsilon. And then I'm left with gamma 2 epsilon. You already see that this simplifies things quite a bit, because now, before you had gamma 1, 2, but now this term here can actually talk to this term here. So it means that there will be cancellations. That's why you need projectors on your Killing spinor. Okay, I'm almost run out of time, but I'm finishing up this computation, so then at least you see the utility of this. So for this term here, we can just replace this by this. And then I can erase all of this, right? So this term starts talking to this. This is still there, so we need to manipulate this term by using all the same things there. So first of all, for this one, you have gamma 2, 2, 3, gamma 2. So again, we use the anti-commutation relation for your gamma matrices to give gamma 2, gamma 3, epsilon. So here I just basically switched the order of these two matrices because again they anti-commute. And then here I can use this projector here, right? So then I can just, this I have minus I gamma 2 3 epsilon equals epsilon. I can introduce like an I which is here. So then this term gives just plus gamma 2 epsilon. Just check, I might have made some typos, but in general that's what you have, gamma 2. So you can just erase all of this. I think also you need to use this I here. So then I can erase this I and then erase this total. So you have 2 over R. I'm just simplifying things a bit. And this I can just erase. So by using these projectors, I've made it such a way that all these terms here have only the gamma 2. Which means that they will just talk to each other, will be cancellations, and then the solution can be found, and this equation can be solved.
I got a little bit lost. I know that you're doing algebraic substitutions now.
Yes.
But why is it that the projections have to be zero on 1 and 2?
I don't know. This is something. Oh, sorry. Again. Okay. Maybe. Sorry. I made a bit of time. Was this the? So these are just projections that you impose on your. You need to make an ansatz for your Killing spinor. So you need to make an ansatz for epsilon, and just by staring a lot at your equation, you come up with some projectors in such a way that all these terms talk to each other. It's a guess that you make. It's a guess that Romans made first that allow this supersymmetry variation to be solved.
Why is it allowed to make such guess?
Because in general, you're Killing spinor, so your parameter epsilon is arbitrary at this moment. You just want to find one that works. Yeah, you just want to find one in such a way that you can solve the equations.
Okay. And that's the reason why it's imposed only on gamma 2, 3 and not on the other one.
I mean, I'm imposing two projectors, so two projections. So epsilon should solve this equation here, and also this.
Okay.
The more
So gamma 1, 2, but we didn't make the projector in gamma 1.
no, exactly. So you need to impose. Let's say, of course, the more projectors you impose, the more you can make the terms talk to each other, because you impose more constraints. But you want to impose the least amount of them in such a way that this is satisfied.
Okay.
Yeah, yeah.
Another basic question is how does gamma 1, 2 become gamma 2 in the...
Because you are using this one. So we first had gamma 1, 2. So you flip, since the gamma matrix is anti-commute, you flip these two, so you make it into gamma 2, 1. It gives a minus sign. And then gamma 1 over epsilon gives you epsilon. So you can reabsorb the gamma 1 and turn this into gamma 2.
This notation,
Yeah, sorry, it's like
gamma
5.
what does the notation of
Yes, maybe I didn't explain. So gamma 1, 2, so gamma AB is equal to gamma A, gamma B minus gamma B, gamma A over 2. I'm skipping a few passages. So by rearranging, yeah, given this definition here, if you rearrange this thing, you can actually, yes, sweep this thing and add a minus sign. Okay, this is the normal, I think, anti-symmetrization of gamma B in general. Okay, almost there. So we have, so we are almost there solving the Killing-Spinor equation. So you see that d theta epsilon, and then we can group everything into a big bracket. This one, okay, again, I'm gonna write it again. Plus 1/2 GR plus 1/2R. All of this multiplies gamma 2 epsilon equals 0. I hope I didn't make any mistake. So this, okay, also has H. Okay, I think, okay, probably no typos. So you can automatically see here that if you put M equals 0 and H equals 1/2G, this thing is 0. Because basically you will have here 1/2 GR plus 1/4 GR, and this thing here becomes a square, right? Becomes G squared R squared plus 1. This is set to 0, and this will become 1/4 G squared R squared. If you take the square root of this thing, it really gives GR plus 1/2 GR. Okay, I'm just taking, I plug in these parameters here, I get this, and this is equal to this is equal to this squared. And so under the square root, I just have this factor here. This thing with the minus 1/2 in front exactly cancel this one. So it means that your Killing-Spinor equation is satisfied with these particular parameters. Exactly, yes. So I can just impose that my Killing-Spinor doesn't depend on theta. It will depend on, in general, in some other coordinate. It will depend on R and on T, for instance. But I can just impose that my Killing-Spinor does not depend on the angular coordinate, and the rest of the things is taken care by the projection and by the parameters that I plugged in. They're just the parameter. If you want to see that this is satisfied, then this holds. You just, yeah, you can see, like you can plug it into Mathematica and so on, and you see that for this choice, this is satisfied. And so, yeah. Which one? This one. No, in general, it is satisfied for a specific choice of spinor. Okay. So it depends. I will tell you in the next class, because I went a bit over time. But in general, you have different sets of parameters, and you have different, that correspond to different sets of projectors on your Killing. So for, you will have different solutions which are supersymmetric. Each one of them will have a different projectors, maybe. They will preserve a different amount of supersymmetry. But the bottom line is that you can find constraints on the parameter, and you can find the form of epsilon in such a way that all the components, now we have only done the theta. If you want, at home, I give you all the possible data to figure out also the other components, because indeed you have also the TR and phi component. You can automatically see that they are satisfied, and the Killing-Spinor, I'm going to show you here the final answer. The Killing-Spinor will be like, we'll have this form here. P minus, yes. Why I put minus? 1, P minus I gamma 2, 3, epsilon 0. So where epsilon 0 is just a constant spinor. So this is like, so a spinor like this satisfies all components of the Killing-Spinor equation. It tells you that your solution with these parameters here is supersymmetric, and also it preserves actually 1/4 of supersymmetry, because each projector that you impose on your spinor halves the amount of supersymmetry preserved. So you have 1/2 multiplied 1/2 is equal to 1/4. So this solution will preserve 1/4 of supersymmetries. And the last thing that I'm going to say is that in general, we canceled here, we saw that we canceled the component of the spin connection with a contribution due to the gauge field. And this means that you're performing the so-called topological twist on your solution. This is a particular way to solve the Killing spinor equation that will have, let's say, will have some consequence at the level of how supersymmetry is preserved also on the field theory side when you do the microstate counting. So, okay, I think that this is something that I want to end up here. So just to recap, we have seen that for certain solutions, you can have supersymmetry preserved by solving these equations. You have to impose some projectors. You have to really determine the parameters, but then your solution is exactly like supersymmetric. So I will deal with these solutions and with the free energy and the entropy and the microstate counting in the next class.
Any more questions? No? I have one question and one comment.
Yes, yes.
So my question is, say that now I start throwing matter inside the black hole.
Mm-hmm.
Should I understand that the black hole is going to increase the magnetic charge in order to preserve SUSY, or it's going to generate some mass and it's going to break SUSY?
So I think in general, well, let's say if you, so you will need to consider a theory where there are also scalar fields and so on and so forth. So your supersymmetry variation will incorporate also scalars and so on, and then you will need to solve the Killing spinor equations again, I think, in order to determine whether. We will see. Yeah, I wanted to show you this as well in the next, but I don't have a lot of time. It turns out that if you add scalars, you can maintain the same projectors, the same very, very similar constraints on the parameters, and you still find a Killing spinor which is very similar to this. So the form of this kind, this is called topological twist, is somehow something that is universal. Even if you add scalars or add further matter, you can still find this sort of preserving spinor which preserves supersymmetry. So it's something that is it's somehow a general technique that is valid also in higher dimensions and so on. It has widespread application.
I have a question. Here. I'm just curious, when you mentioned this solution that has a black hole, right? Is it an original solution of the equations, or you have a delta source for the equations?
Okay, no, I mean, okay, first of all, I cheated a bit because the solution that we have, it's actually, so we started from the Reissner-Nostrom solution, but the solution, if you plug in these parameters here, you will see that actually you don't have a black hole, you have a naked singularity. So okay. I told you about black holes, but the parameter that preserves supersymmetry give you a naked singularity. To have a well-defined black hole, you will need to consider a Reissner-Nostrom solution with a hyperbolic horizon, with a different topology of event horizon. This is something, it's a bit of a detail that I meant to explain in the next class. Okay. But to come back to your point,
do you have
I mean, the delta, it's like where once you solve for the Schwarzschild solution.
But in Schwarzschild, you do have a delta, right?
Yeah, it's like, I mean,
so your solution is not just R mu nu equals 0 everywhere. It has a delta at the origin, right?
Yeah, if you want to consider in the distribution sense, yes. There's a delta function at the origin where the mass is. But throughout the entire solution, you just solve the Einstein's equation with 0. Like, or in this case, with the Maxwell field strength, with the stress energy tensor of the Maxwell field. But it's the usual, it's the same thing as in the Schwarzschild one. Okay. You consider a point like object at the singularity. So yeah, a distribution, something which is supported at R equals 0.
Should I consider that solution like a vacuum, or it's just a ill-defined solution because it has a naked singularity?
Yes, so you will see, for instance, if you add scalars, if you add rotation and so on, a very similar structure to this arise, and also you manage to cloak the horizon. So I will not consider really this as some sort of like a vacuum state, given it that it has a singularity. It's more like a mist black hole in this sense. Of course, you don't want to work on this because you have zero entropy, but as soon as you add scalars and so on, you will have a horizon right away, and then you will be able to work with that.
Well, I have
I have one. You have more constraints to be consistent with the 11-dimensional truncation, or ever you can embed these solutions in 11 dimension?
No. In general, whenever you have such a truncation, so yeah, people worked out all these truncations of M theory on various manifolds, like Sasaki-Einstein manifold. Whenever you have a solution in 4D, you automatically are, let's say, guaranteed that it's a solution also of 11D without any further constraint. They give you a recipe to, they give you basically the full 11-dimensional metric. So the full 11-dimensional metric will have a 4D part, which will be the metric of the black hole. And then you have some non-trivial 7-dimensional manifold that compose your 11-dimensional metric. But the recipe is already in the paper. So basically, you automatically are guaranteed that if you find a solution here which is supersymmetric, it uplifts to 11D and it's supersymmetric also there. Actually, you have that whenever you have charge in lower dimensions, so the gauge field A phi and AT in 4 dimensions uplift in 11D as angular momentum. So the interpretation in terms of D branes or M branes of these black holes will be, let's say, in the case where you have an electric solution, an electric solution will be basically spinning branes in 11D. Once you have magnetic field, this magnetic field in 11D will act as some sort of a nut charge. So it's like non-trivial vibration between the angular coordinates on your 11-dimensional metric. But yeah, so to answer your question, you're guaranteed, you have in 4D, it automatically is a solution, supersymmetry solution of 11D.
Okay, sorry. I'm always confused with the counting of supersymmetries in this kind of theories, because you started with n equals 2.
Yes.
And you impose 2 projectors that breaks the supersymmetry to 1/4, right? So in this case, how many supersymmetries?
So I will have, in general, so I will have, I think, 2 real supercharges that are preserved, if I'm not mistaken. I also getting confused sometimes.
Depends on the conventions.
Depends on the conventions, yes.
Okay.
But in general, you have 1 spinor, you impose, because I repackaged also, my spinors into complex spinors. So in general, a solution, exactly. So you will have 1/4 will have 2 real supercharges or 1 complex.
Just a quick comment before Nico gets angry for the students. So if you got lost with all of the fermion manipulation and whatnot, a really good reference for all of these and useful identities is the Supergravity book by Van Proyen.
Yes.
And then there's also a paper in the archive that's something like Supergravity or tools for supergravity, also by Van Proyen, many useful identities from gamma matrices and so on that you can use to follow this.
Thank you. Yes, great. If you need also further reference, I'm happy to provide.
So we're running a bit late. Let's thank Chiara again. Go for the coffee. We meet again at 11.